In mathematics, the special unitary group of degree n, denoted SU, is the Lie group of n times n unitary matrices with determinant 1. The group operation is that of matrix multiplication. The special unitary group is a subgroup of the unitary group U, consisting of all n times n unitary matrices. As a compact classical group, U is the group that preserves the standard inner product on Cn. It is itself a subgroup of the general linear group, SU-UGL. The SU groups find wide application in the standard model of particle physics, especially SU in the electroweak interaction and SU in quantum chromodynamics. The simplest case, SU, is the trivial group, having only a single element. The group SU is isomorphic to the group of quaternions of norm 1, and is thus diffeomorphic to the three-sphere. Since unit quaternions can be used to represent rotations in three-dimensional space, there is a surjective homomorphism from SU to the rotation group SU whose kernel is plus I minus I. SU is also identical to one of the symmetry groups of spinors, spin, that enables a spin or presentation of rotations. Properties. The special unitary group SU is a real Lie group. Its dimension as a real manifold is n2-1. Topologically, it is compact and simply connected. Algebraically, it is a simple Lie group. The center of SU is isomorphic to the cyclic group zinc, and is composed of the diagonal matrices zeta I for zeta and nth root of unity and I the n times n identity matrix. Its outer automorphism group for n3 is Z2, while the outer automorphism group of SU is the trivial group. A maximal torus, of rank n-1, is given by the set of diagonal matrices with determinant 1. The WEYL group is the symmetric group Sn, which is represented by sign permutation matrices. The Lie algebra of SU, denoted by SU, can be identified with the set of traceless anti-Hermitian n times n complex matrices, with the regular commutator as Lie bracket. Particle physicists often use a different, equivalent representation. The set of traceless Hermitian n times n complex matrices with Lie bracket given by minus I times the commutator. Infinitesimal generators. The Lie algebra SU can be generated by n2 operators, I, j equals 1, 2, n, which satisfy the commutator relationships for I, j, k, equals 1, 2, n, where delta jk denotes the Kronecker delta. Additionally, the operator satisfies, which implies that the number of independent generators of the Lie algebra is n2-1. Fundamental representation. In the defining, or fundamental, representation of SU, the generators TAR are represented by traceless Hermitian matrices complex n times n matrices, where the f are the structure constants and are antisymmetric in all indices, while the D coefficients are symmetric in all indices. As a consequence, we also take as a normalization convention adjoint representation. In the dimensional adjoint representation, the generators are represented by times matrices, whose elements are defined by the structure constants themselves. N equals 2. SU is the following group, where the overline denotes complex conjugation. Now, consider the following map, where M denotes the set of 2 by 2 complex matrices. By considering C2 diffeomorphic to R4 and M diffeomorphic to R8, we can see that phi is an injective real linear map and hence in embedding. Now, considering the restriction of phi to the three-sphere, denoted S3, we can see that this is an embedding of the three-sphere onto a compact submanifold of M. However, it is also clear that phi equals SU. Therefore, as a manifold, S3 is diffeomorphic to SU, and so SU is a compact, connected Lie group. The Lie algebra of SU is it is easily verified that matrices of this form have traced 0 and are anti-Hermitian. The Lie algebra is then generated by the following matrices, which are easily seen to have the form of the general elements specified above. These satisfy U3 U2 equals minus U2 U3 equals minus U1 and U2 U1 equals minus U1 U2 equals minus U3. The commutator bracket is therefore specified by the above. Generators are related to the Pauli matrices by U1 equals I sigma 1, U2 equals minus I sigma 2, and U3 equals I sigma 3. This representation is routinely used in quantum mechanics to represent the spin of fundamental particles such as electrons. They also serve as unit vectors for the description of R3 spatial dimensions in loop quantum gravity. The Lie algebra serves to work out the representations of SU n equals 3. The generators of SU T in the defining representation are, where lambda the Gell-Mann matrices, are the SU analog of the Pauli matrices for SU. These span all traceless Hermitian matrices H of the Lie algebra, as required. They obey the relations. The F are the structure constants of the Lie algebra, given by, while all other not related to these by permutation are 0. The symmetric coefficients D take the values. As a topological space, SU is a direct product of a 3-sphere and a 5-sphere, S3 S5. A generic SU group element generated by a traceless 3×3 Hermitian matrix H, normalized as TR equals 2, is given by where, for elementary representation theory facts, Lie algebra structure. The above representation base is generalized to n greater than 3, using generalized Pauli matrices. If we choose an particular basis, then the subspace of traceless diagonal n times n matrices with imaginary entries forms an dimensional Cartan subalgebra. Complexify the Lie algebra, so that any traceless n times n matrix is now allowed. The weight eigenvectors of the Cartan subalgebra itself, as well as the matrices with only one non-zero entry which is off-diagonal. Even though the Cartan subalgebra H is only dimensional, to simplify calculations, it is often convenient to introduce an auxiliary element, the unit matrix, which commutes with everything else for the purpose of computing weights, and that only. So, we have a basis where the ith basis vector is the matrix with 1 on the ith diagonal entry and 0 elsewhere. Weights would then be given by n coordinates and the sum over all n coordinates has to be 0. So, SU is of rank n-1 and its Dynkin diagram is given by n-1, a chain of n-1 vertices, O-O-O-O-O. Its root system consists of on-roots spanning a n-1 Euclidean space. Here, we use n-redundant coordinates instead of n-1 to emphasize the symmetries of the root system. In other words, we are embedding this n-1 dimensional vector space in an n-dimensional one. Thus, the roots consists of all the n permutations of. The construction given above explains why. A choice of simple roots is its Cartan matrix is its WEYL group or Coxeter group is the symmetric group Sn, the symmetry group of the simplex. Generalized special unitary group. For a field F, the generalized special unitary group over F, SU, is the group of all linear transformations of determinant 1 of a vector space of rank n equals p plus q over F which leave invariant and non-degenerate Hermitian form of signature. This group is often referred to as the special unitary group of signature PQ over F. The field F can be replaced by a commutative ring, in which case the vector space is replaced by a free module. Specifically, fix a Hermitian matrix A of signature PQ in GL. Then all satisfy. Often one will see the notation SU without reference to a ring or field, in this case the ring or field being referred to as C, and this gives one of the classical Lie groups. The standard choice for A when F equals C is, however, there may be better choices for A for certain dimensions which exhibit more behavior under restriction to subrings of C. Example: an important example of this type of group is the Picard modular group SU, which acts on complex hyperbolic space of degree 2. in the same way that SL acts on real hyperbolic space of dimension 2. In 2005, Gabor Francisks and Peter Lax computed an explicit fundamental domain for the action of this group on HC2. A further example is SU, which is isomorphic to SL. Important subgroups. In physics, the special unitary group is used to represent bosonic symmetries. In theories of symmetry breaking, it is important to be able to find the subgroups of the special unitary group. Subgroups of SU that are important in gut physics are for p greater than 1, n minus p greater than 1, where times denotes the direct products in U, known as the circle group, is the multiplicative group of all complex numbers with absolute value 1. For completeness, there are also the orthogonal and symplectic subgroups, since the rank of SU is n-1 and of U is 1. A useful check is that the sum of the ranks of the subgroups is less than or equal to the rank of the original group. SU is a subgroup of various other Lie groups, see spin group, and simple Lie groups for E6, E7, and G2. There are also the accidental isomorphisms. SU equals spin, SU equals spin equals SP, and U equals spin equals SO. One may finally mention that SU is the double covering group of SO, a relation that plays an important role in the theory of rotations of two spinors in non-relativistic quantum mechanics. Remarks. For a characterization of U and hence SU in terms of preservation of the standard inner products on N, see classical group. For an explicit description of the homomorphism SU-SO, see connection between SO and SU. SP is the compact real form of SP. It is sometimes denoted USP. The dimension of the SP matrices is 2n times 2n.